So we're starting with 4-2 alpha. Right. And let's look at a question from the end. So this is question 53 from the end of the section. And then you can't do that yet, but you can think about it. And the question says, y equals the cosine of x. Right, so the cosine of x looks like this. Okay? So y equals the cosine of x. The mean value theorem guarantees is somewhere between 0 and pi over 3. Cosine 0. What's the cosine of 0? You see what I'm doing? Am I just look silly?
1.
It's root 4 over 2. Yes, it's 1. Right? You notice the head in the hand chart? Root 4 over 2. Now we're in the root side. And at pi over 3, here, root 1 over 2. So this is the point 0, 1. Let's write this. When x is 0, the cosine is 1. When x is pi over 3, the cosine would be 1/2. Make sense? Hopefully, because you're going to use an H chart the entire course. So all we did, we didn't do any work, we just set the problem up. So the derivative must be one of those choices. And looking ahead, we'll come back to the problem. Looking ahead, just so you know, there were no multiple choice questions last May. The entire AP test was 2 extended FRQs. But if we get back to multiple choice questions this year, there's only 4 choices, not 5. So in the textbook, that was before they edited the AP test. They moved it down to 4 choices. Right? So here's the mean value theorem. I have an analogy for the mean value theorem. Are you interested, or you think my analogies are boring? No one? They are boring? Okay, so here's the analogy. Ready? Pretend you live near the old CVS. Which one is the old CVS? They're both old to you. But I remember the new one being built. Which one? The one on Norwinden is the old one. Okay? So Norwinden is the old CVS. How far away is that from here?
That's street food.
Let's say 2 miles. We can round it to 2 miles. It might not be 2 miles, but let's just say it's 2 miles. You good? And your parents let you drive their car to this school. And it took you 10 minutes to get here. 10 minutes. What was your average velocity for the trip? If it takes you in miles per hour. If it takes you 10 minutes to travel 2 miles, what is your average velocity for the trip? Not breaking my time. You can go 2 miles in 10 minutes. How far can you go in 60 miles? 12 miles per hour, Andrew, correct. That is your average velocity, your average speed, which is the absolute value velocity. Your average speed for the trip is 12 miles an hour. Is that logical? The mean value theorem says this. At some point on your trip from the old CVS to here, you must have been going exactly 12 miles an hour. If 12 miles an hour was your average speed, at some point you must have been going exactly 12 miles an hour. Make sense? It does. Why? Because if you start from a dead stop, this is saying that your trip is continuous and differential. Then in order to get the average speed to 12, at some point, speedometer is going to have to go above 12 to make the average speed. That's what this is telling you, right? The mean value theorem. That's the example you need to think about. And then there's a really user-friendly example, which uses the number 2 most user-friendly parent graph, which is y equals x squared. So I built this, I don't know, H chart up here. And in the book, they talk about points A and B, which I find to be confusing because C is between A and B. It's not like any alphabet alphabet. So I took out the A and B and called them x sub 1 and x sub 2 as you go from left to right. So in this case, x sub 1 is 0 and x sub 2 is positive. Okay? In the mean value theorem we talked about is saying this. The average change would be this value, the height at x sub 2, take away the height at x sub 1, difference of the y's over difference of the x. The instantaneous change would be the value of the derivative at this point between those two values. And at some point in the interval, they're the same. The instantaneous change, what's on your speedometer at that moment, equals the average change. So here's the example. Like I said, number 1, most user-friendly parent graph. Number 2, sorry, y equals x squared. So there's a picture in the book. Here's the picture. We're on page 197. The blue graph is y equals x squared in quadrant 1. And you want the change over the interval from 0 to 2 inclusive. So the average change is the slope of this black secant line. And what the theorem is telling you is that at some point in that interval, the tangent line will be parallel to the secant line. If the tangent line is parallel to the secant line, they have the same slope. And that's what a derivative is. It's the slope. So here's how we did this. Y equals x squared without the picture. Y equals x squared. The interval 0 to 2, brackets mean inclusive. Those points count. There's my H chart. 0 squared is 0. 2 squared is 4. So the average change is 4 take away 0, but 2 take away 0 is 2. The instantaneous change is the value of the derivative. You differentiate x squared, you get 2x, power rule. 2x has to equal 2. The average change, sometime between 0 and 1. So x has to be 1. Right? At 1, the derivative is 2. At 1, the height of the function is 1. So this is, ready? This is 1. Average change has to be equal to the instantaneous change. And this is when. At 1, the average, the instantaneous change is 2, which equals the average change. So that's your model. We're going to pause this. Use that model to go to problem number 1. Ready? So here is a graph in blue. Right? Here's the book. The interval is 0 to 1. The derivative of this is linear. Is that quadratic? So the derivative is going to be first degree. Here's my table. At 0, cover-up method, the function gives you -1. at 1, 1 squared plus 2, take away 1, gives you 2. So the average change is 2 take away a negative 1, which is 3, over 1 take away 0. The average change is 3. So because this function is continuous and differentiable on the interval 0 to 1, at some point the derivative must equal to 3. So we set the derivative equal to 3. Now for one problem. Add a negative 2 to both sides, divide both sides by 2, and you get 1/2. So at 1/2, the derivative, the instantaneous change, matches the average change. The height of the graph is 1/4. So that means if you go on this picture, the red line is the secant line. It represents the average change. But if you trace the blue graph and went 1/2 to the right, up 1/4, the tangent to the blue graph at that point, 1/2, 1/4, would be parallel to the red secant line. That's what this is about. It's not the best windows, but you see what's happening. Now, this is a little bit misleading. What's misleading about the example and the problem in the back of the exercises is both times the when is dead center on the table. Don't count on that. It's not going to be dead center on the problem 53 that we're going to come back to. Example 2. So example 2, go back to the book. Here are 2 times that the conditions are not met. When I look at this picture, you're familiar with this picture. This is y equals the absolute value of x, and moved up 1. So the pre-image is y equals the absolute value of x. The image is y take away 1 equals the absolute value of x. But from the beginning of chapter 3, this is not differentiable when x is 0, because the slope from the left, -1, is not equal to the slope from the right, +1. You have a corner there. You're not responsible for that definition, that vocabulary word, but it's not differentiable when x is 0. And in this picture, what is at 1, 1 is in the domain. So this function has discontinuity when the input is 1. So this thing is not continuous, and this one is not differentiable. And if you have either one of those, then the conditions for the mean value theorem are not met. Well, you gotta be careful. You gotta look for that first. You don't want to be doing the calculus if the conditions aren't met. So what are we going to use this for? Well, one thing we'll use it for is this. Increasing and decreasing functions. You already knew this. Okay? You knew this from the big derivative puzzle. But we're going to quantify here. If the parent graph is increasing, the derivative is positive. If the parent graph is decreasing, the derivative is negative. So how can we justify that? Well, here we are. Here's the mean value theorem right here. This is the instantaneous change. That's the average change. And we're going from left to right. So the x2 is greater than x1. In this case over here, x2 is 5 and 3, x1 is 0. You're going from left to right. So this is larger than that. 2 is larger than 1. Now what? All right. We're going to clear the fractions and multiply this to both sides of equal sign. you're going to get the derivative times this thing, which we know is always positive, because it's the x value to the right, x of 2 take away x of 1. What about a positive number? Whenever we multiply it by, the signs, the SIGN stays the same. A positive times a positive, a positive. Positive times a negative is a negative. So if the derivative were negative, and you multiply it by a positive, the left side would be negative. And if the left side's negative, the height at 2 take away the height at 1 has to be negative. Which means the graph's falling right here, right? I look over here and say, here's 0, here's pi over 3. There's this height, there's that height. The height at 2, the second input, is lower than the height at 1. The height, f, when x of 2 is the input, you're taking away a larger value for it to be negative. This height, take away that height, it's negative. Graph's falling. If the derivative is positive, then that must be positive. So we say, in conclusion, something you already know, just to justify. If the derivative is negative, then the parent graph is falling. If the derivative is positive, then the parent graph is rising. But that was based on this. In the book, they call these points A and B, which I just think is not helpful. Okay? So, let's go back here. Let's finish this problem. Because if the slope were 0, the line would be horizontal. Yes? What else is out? E's out. Why? Thank you, Emma, because E's positive. So you could do this and say, well, at least I can narrow it down. If you can narrow it down 2 answers in May, there's only 4 to choose from. Of A, B, and C, which answer is correct? A. Emily ate her Wheaties today. Here is the table. Just like over there. So I want the average change. Now, if you look over here, I subtracted down. It doesn't matter if you subtract down or subtract up. You just can't mix and match. So I did 1, take away a half. Divided by 0, take away 5 or 3. Now we're here. I want to know what this is. So I have 1/2 divided by a negative 5 or 3. How do you divide by a fraction? You invert and multiply. Yes, I know. Why does it work? Never bother you? Why just following steps? It works because if we multiply this, the question, by 1, in the form of negative 3 over pi divided by negative 3 over pi. What's in red is something divided by itself. Everything divided by itself is 1. So it makes the denominator, it's a reciprocal, makes the denominator 1. The red thing is 1, and you multiply across, that's 1. So you don't do this. It's not efficient. So the shortcut is just take that invert and multiply. But that's why it works. So what do you get? Negative 3 over 2 pi. what happened there. This is the what? There's some value in that interval where the cosine equals -3 over 2 pi. The instantaneous change. Also, where the derivative of the cosine. What's the derivative of the cosine? Oh, what's the derivative of the cosine? Negative sign. So at some point, ready, the negative sign has to be -3 over 2 pi. Second sign of 3 divided by 2 pi. It's that many radians, which is between 0 and pi divided by 3. Yep. Except you notice here, this is, and for the point of the test, we'll say 3 decimal places, 0.498. This is the what, that is the when, and this value is not halfway between there like it was on the example and on problem number 1 in the back. Okay, so that's all for 4-2 alpha.